Hello everyone, welcome to the solution of LeetCode problem 684 named redundant connections. In this problem, a tree is an undirected graph that is connected and has no cycle. Now, you are given a graph that is started as a tree with n nodes level from 1 to n with one additional edges. Now, the added edges has two different vertices chosen from 1 to n. And was not an edge that is already existed. Now the graph is represented as an array of edges of length n, where edges of I is A of I and B of I, indicates that there is an edge between the nodes A of I and B of I in the graph. Now we have to return an edge that can be removed so that the resulting graph is a tree of n nodes. And if there are multiple answers, we can return the answer that occurs last in the input. Now let's consider the first example. Here the edges are 1, 2, 1, 3 and 2, 3. And if we connect the edges into three nodes 1, 2 and 3, the graph will look like this. So here, if we remove the edge 2 and 3, the graph will not contain the cycle, hence 2 and 3 will be the output. And in the second example, the edges are 1, 2, 2, 3, 3, 4, 1, 4 and 1, 5. Now, it can be possible that we remove the edge 1 and 4. So, suppose the connection between 1 and 4 does not exist. So, in this case, the graph does not have any of the cycles. So, 1 and 4 will be the desired output. I hope you understood the problem statement. Now, let's move on to the algorithm. In this problem, to understand the algorithm, we have taken the second examples. The edges are 1, 2, 2, 3, 3, 4, 1, 4 and 1, 5. So we have to build the graph. After that, we have to remove one of the edges such that the graph becomes the tree. Now basically, as it is a graph problem, we have to understand in which graph algorithm should we use. So we can use the disjoint set union data structure to solve this problem. In the DSU, basically, we will keep track two of the arrays. One is the ultimate parent, another is the size. And as we will building the graph, we will calculate the ultimate parent of the node and the size of the current tree. And we will add the tree with the smaller size to the tree with the greater size. And the ultimate parent of, suppose it is V and it is U. So here, the parent of U is V. Suppose V has another parent W. So the ultimate parent of U is W, which is the top level parent. And similarly, the ultimate parent of V is also W. And the size of a tree is the number of nodes connected in the tree. So here, now let's see how can we solve this problem by using the disjoint set union data structure. Basically, we are given 6 nodes here. Now, all of the nodes are separated and each of the node is parent to itself. That means 1 is parent to itself, 2 is parent to itself, 3 is parent to itself, and so on. Or we can say that all of the node is ultimate parent of itself. So here the ultimate parent of 1 is 1, the ultimate parent of 2 is 2, ultimate parent of 3 is 3, ultimate parent of 4 is 4, 5 and 6. Now, as all of the nodes are separated, let's consider them one of the tree, and this tree has size of the 1. Similarly, this tree has the size of the 1. So, the tree presented at index number 1 has size of 1. Similarly, all of the tree will be size of 1. Now we have to do two things. One is path compression, another is union. So here, to apply the union, there are two algorithms. One is union by rank and another is union by size. So here we will apply the union by size. Both of them are in the same complexity, so you can use any of them. In this problem, I am using the union of size. And the path compression basically means, suppose there is a node 1 which has a children 2 and 2 has a children 3. Suppose here we have to decide what is the ultimate parent of 3. The ultimate parent of 3 is 1. So how can we get the answer? To get the ultimate parent of 3, we should ask 2, what is the ultimate parent of 2? The ultimate parent of 2 is 1. So 1 will be returned here and 1 will be returned here. So to get the ultimate parent of 3, we have to call the function into the ultimate parent of 2. This is costly. What if we discard this edge between 2 and 3 and connect 1 and 3? So here, by doing so, if we want to get the ultimate parent of 3, we can simply get is 1. Here, we cannot go via 2. So this is the path compression. That means we are reducing the number of calls to get the ultimate parent of a node. Now, let's consider the first stage between 1 and 2. So we have to connect the node 1 and 2. So here, now, suppose 1 is the parent here and 2 is the children. So what is the ultimate parent of 2? The ultimate parent of 2 will become 1. Now, the size of the 1 will increase by 1. That means here, the tree presented at root 1 has size of 2. That means there are 2 nodes presented. Now, for this connection 2 and 3, we have to connect it, and the ultimate parent of 3 will be equal to the ultimate parent of 2. And what is the ultimate parent of 2? It is 1. So, the ultimate parent of 3 will become 1. Now, we have to increase the size of 2. So, the size of 2 will become 2. Because it has 2 nodes under it. One is 2, another is 3. Now, for this connection 3 and 4, we have to connect 3 and 4. And what is the ultimate parent of 4? The ultimate parent of 4 will be ultimate parent of 3. So here the ultimate parent of 3 is 1. So the ultimate parent of 4 will be 1. And the size of 3 will be increased by 1. Now there is a connection between 1 and 4. But wait, if we connect the node 1 and 4, it will form a cycle. That means we cannot connect this node. So how can we decide if both of the 1 and 4 has the same ultimate parent? That means we cannot connect node 1 and 4. So now we have seen that the node 1 has ultimate parent of 1, the node 4 has ultimate parent of 1. That means if we connect two nodes which has the same ultimate parent, it will form a cycle. So this is our desired output. And this is how we basically solve this problem, by using the path compression and union by size, which utilizes the disjoint set union. Now let's wrap up the algorithm. Here, by using the DSU, we will build the connection, and if any of the connections, we have basically two nodes, first node and the second node. And if the both of the nodes has the same ultimate parent, we can say that if we connect these two nodes, they will form a cycle. So if we remove these two nodes from our graph, the graph does not contain any of the cycle. Now, I hope you understood the algorithm. Now let's move on to the code. In this algorithm, to understand the code, we have taken a vector named parent and size. Now, we are initializing the vector parent and size here. The parent of I will be equal to I, and the size of I will be equal to 1. Now, this is our find parent function. Here, we will taking a node as a parameter, and if the node is equal to the parent of node, we have to return the node. Otherwise, we have to return parent of node is equal to find parent, parent of node. That means here we are storing the recursive return value into a array, and finally we are returning the find parent of the node. Now this is the union by size. We are taking two nodes u and v, and here we are calculating the ultimate parent of u and ultimate parent of v, and if both of them are equal, we cannot do anything. Otherwise, if the size of the ultimate parent of u is less than the size of the ultimate parent of v, here we have to attach the smaller tree, which is u, to the greater tree v. So the ultimate parent of u will become the ultimate parent of v, and the size of the ultimate parent of v will be increased by the size of the ultimate parent of u. Otherwise, we have to assign the ultimate parent of v to the ultimate parent of u. So the ultimate parent of v will be equal to the ultimate parent of u, and the size of the ultimate parent of u will be increased. Now here in the main function, we are given the edges, and we are calculating the size of the edges, which is equal to n, and we are passing it into the DSU constructor. Now for each of the edges, if the ultimate parent of x is equal to the ultimate parent of y, we have to return x and y. That means if we discard the edge between x and y, the cycle will be removed and the graph will not contain any of the cycle. So we have to return it. Otherwise, we have to connect the node x and y by using the union by size method. Finally, if we do not able to return any of them, we have to simply return an empty vector. I hope you understood the code. Thank you everyone for watching the video. We will get back soon with another LeetCode solution.